Hello. Today we're going to talk about the second part of Chapter 4, and that is reactions in aqueous solutions and the redox portion. So the redox section. So open up your PowerPoints, please. We're going to skip towards the back. Just to remind you what we're doing today, I'm going to go over how our oxidation numbers determine one of our benchmarks. If I get to it, we're going to try and understand oxidizing reducing agents. We've got a lot more work to do, as these other benchmarks show you with redox, but this is our day one intro, so we can take a peek at what we're going to learn ahead of time, and then eventually we'll get to the rest of this. So we're going to be doing this in the lab environment, but we're also going to be first learning about these oxidation numbers, so we can balance some simple and then very complex reactions. All right? So, what do we know about oxidation and reduction? Chemists are lazy, let's abbreviate that. Redox. Oxidation, reduction, reactions. RXN reactions. These are very powerful reactions. And that's what I'm going to show you first. And if you want to skip past all these videos I'm going to show in a minute, feel free. However, these are very powerful. Why we want to be able to do this redox is so we can balance some complicated reactions. So, let's see what this looks like. And again, it would be perfect world. I would be able to show you all these demos, but it's much easier for me to show you all this on the movies. So let's take a peek at hydrogen and oxygen balloons. Okay, so you can see this is always fun anyway. Hydrogen balloon. Guess what? Pops, right? And then they're going to step through on some of these videos. Look at the powerful reaction. We say chemistry 2 is not rocket science. Well, this is, okay? Hydrogen and oxygen mixture. That's very powerful, okay? Again, stepping through it. Now, there's a few more of these videos. This next one, I don't think you've seen a lot of reactions that are catalyzed in light. So watch this one. Okay. So next is steel wool and oxygen. So steel wool is just like a Brillo pad, heated up. It really is iron, and this is an oxygen environment. And it just doesn't burn. It burns very nicely. So we can write their reaction, and that's easy to predict what our product is in there. However, what happens is that the iron and oxygen changed oxidation numbers. And that's what we're going to learn. Now, again, powerful. Okay, the next one, not so important. Let's go back here to the titles. Sodium and chlorine. Let's watch sodium and chlorine. Now, we all know what salt looks like. Okay, we all know what salt looks like, but how is it made? Right? Well, it's found in the earth. However, if I want to synthesize it in the lab, sodium, here's a chlorine environment, and put that chunk of sodium in. And again, I can't do all these reactions, so I'd rather show it to you this way. Now, we know sodium will react with water, but what happens with that chlorine environment? And again, note the products. It was salt. It was salt. Now I'm going to skip past these side reactions. If you want to, okay, you can review this and watch some of the side reactions. But there's a few more you probably want to see. And what happened? Okay, we like magnesium. Okay, you've done this a ton of times, magnesium in a Bunsen burner. So magnesium heated, don't look at it directly, right? Look out of the side of your eye. It's okay on video. Okay. Fireworks. All of a sudden the white in fireworks, we understand it comes from our magnesium. Okay, now magnesium with carbon dioxide. That's what we'd like to see. Make carbon dioxide chunk here. Here's the dry ice. Ignite that magnesium and plunge it in. Powerful. We like to do that one a lot. Okay. Note the product. Now, a wood splint, carbon dioxide, predictions. Oh yeah, it goes out. But now, here comes the cool one. Big chunk of dry ice, hollowed out. There's my magnesium. This is cool, literally cool. Dry ice, get it? Note the product in there. Not at all like our reactants. Alright, maybe you're getting bored watching these. Again, you're more than welcome to skip past. Okay. I like this one though. Aluminum and iodine. Al plus I2. So I skipped a few of those. Here's some aluminum and iodine. And just a little water. Pretty purple, right? Okay, wrong one. Play the DVD. This one. Title menu. And go down to the next one. Okay? We like these phosphorus ones. This is phosphorus on the left. The red phosphorus is just like matchbooks. That's what you find on the back of a matchbook. White phosphorus, we don't see much, only in a chem lab. So they're stepping through, nothing here, but we're definitely changing over with the white phosphorus. And all on its own, it's reacting. Okay, not on its own, obviously. Oxygen. Nothing with the phosphorus, on the red phosphorus on the left. I wonder if there's anything we can do. Take a glass rod heated. Oh, sure. Heat on a matchbook will ignite. How about chase some white phosphorus underwater? White phosphorus again, we saw in the previous, in the water, and now watch what happens when we blow some gas in there. Again, little fireworks, powerful. All right, maybe you're a little bored with the others, but this is great. Barking dogs, phosphorus again. White phosphorus. I love that. You think it's going to be louder because it's taller, but it fell off. So sulfur and oxygen. Mainly I want to show you this one so you can see the next one. So sulfur, burning sulfur, what color? When you ignite sulfur, remember the one lab? We ignited our sulfur with our copper. We look for a blue flame. We'll plunge it into an oxygen environment. And we'll make our SO2. But with that very vibrant blue flame. Okay, so we've made some SO2. We've got our sulfur dioxide gas. I know, not that exciting. But again, there's that beautiful blue flame. Now, this is fun, biochemistry. What about a rose? Red rose, oxidation reduction. Once again, there's that sulfur dioxide. That's why we showed you the last one. Now, take that red rose into this sulfur dioxide. And this is the beauty of a video. We don't have to wait. They can 1 minute, 2 minutes, 5 minutes. And we've changed the pigment. In biology, there's a lot of oxidation reduction reactions. Is that how they make pink roses in the florist? No, that's genetics. But chemistry, we can now take that rose and plunge it into, if you missed it, that was nitric acid now. Now we're in nitric acid. After 1, 2 minutes, 5 minutes again, and look what we've done. These are powerful reactions. Whether they explode or change colors, they didn't just happen in a short time. There was some sort of time needed, and they were very powerful. Okay, so just to give you an idea of those, okay, just to give you an idea of what those reactions look like and why we are going to study them and why we're going to study them. So here we go. What we said again is these reactions, and we saw the movies, these reactions are very powerful. How are we going to determine oxidation numbers? Okay. And who is oxidized and who's reduced? And then you're asking yourself, what are oxidation numbers? Remember, whenever you have, we sometimes called it valence sheet. If you noticed, it actually is oxidation / valence numbers of common ions in chemistry. And you've asked a couple times along the way, well, what's the oxidation or what's the valence number of iron? And when we write compounds. And what we know is we would sometimes check this. So this is what we're doing first, is where do we get these numbers and what does it mean if it's oxidized or reduced? Okay, so what do we have to know is that it involves electrons. That was too soon. It involves electrons. And whenever I talk about powerful reactions, when we want to know about that, I think of a powerful animal. And in the animal kingdom, the most powerful animal is a lion. Okay, a lion. And whenever I think of a lion's name, I think of, no, not Mufasa, not Simba. Okay, the one that's the constellation, I think of Leo. And when Leo is trying to be powerful and chase down some animal, he'll say, grrr. So that's how I know if an element was oxidized or reduced. I know Leo grrr. Now, Leo grrr is just a little aid to help you understand that Leo means we're going to lose electrons oxidized. Your element will be if it loses electrons, it will be oxidized. Grr means gain electrons reduced. I want to keep track of that. I want to keep track of that because we want to know if our elements lost or gained electrons in order to move on and balance equations. Your book liked, okay? Your book liked another phrase. It liked oil rig. Okay, oil rig, maybe this works for you, is oxidation involves loss. I'm not a fan of it because what is it a loss of? I like the fact that it's telling me, oh yes, electrons. So rig, if you can imagine, means reduction involves gain of electrons. So that is what you need to understand, is that it's what are we gaining? We're gaining electrons. And again, grr, rig, same thing. Okay? let's take a peek. It says we should peek at this CD, screen 8, okay? And so when I do, this is another redox reaction that you've seen many times.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
So again, there's oxidation reduction reaction, very similar to all those ones we saw in the video. This is what I see out in the parking lot, especially with your beaters. Lots of rust. Really, that's oxidation, but something is being reduced when something's oxidized. So that's why we mentioned that there on that slide, is to go back and peek at that too. Okay, so how do I know these oxidation numbers? Okay, how do I know these oxidation numbers? This is listed in the text. Also, we've tried to summarize with this yellow sheet some of these rules, so you may want to have that out. And when I go through these, I'm going to refer to some of your homework. Here is oxidation number skills sheet with a few more on the back. And then we'd like you to review what I've been talking about on this activity 8.1, answering what's oxidation, what's reduction, and then practicing with a whole mess of these of determining oxidation numbers on the back of activity 8.1. Okay, so what are the rules? And again, they are listed in various places. It says the oxidation state of an atom of an element, when it's all by itself, is 0. So I'll sort of refer back. This will help you with the oxidation number skill sheet. Their sample there is Fe. Fe all by itself is 0. And then we put the oxidation number above the element. O2 is another example. O, it's an element. It happens to be diatomic. It also is 0 for its oxidation number. Rule 2, what if I have an element, and again there's more verbiage to this, but what if I have an element with a charge? So, the oxidation state of an element that actually has a charge. Now this flows down here on this worksheet. An example on your homework is Br1-. Okay? What's the oxidation number of a bromide ion? Don't overthink this. It is 1-. Okay? When an element has a charge, that is its oxidation number. When it's by itself, its oxidation number is 0. Now, these are ones you want to keep track of. Oxygen, 99% of the time, is a -2. 99. So when in doubt, put -2. But when it's in a peroxide, in one of my favorite chemicals, hydrogen peroxide, okay? When it's in a peroxide, there is no way it can be a -2 and then fulfill one of our other rules as we go down, and that is the charge on a compound that does not, the oxidation numbers of all the elements in the compound has to equal 0. In these compounds, it had to be a -1. And I'll show you when we get to that one. But let's just go through these rules. Hydrogen, once again, 99% of the time is going to be a +1. Every once in a while, it will be a -1. And that would be when it's in a metal as a metal hydride. How do I recognize this? Metals have to be, okay, our group 1 and group 2 metals are always going to be the usual oxidation number that we see in that group. Calcium is a +2. Somebody has to be a negative in order to fulfill my next rule. So that means when I have hydrogen in that second position with a metal in the first, then hydrogen is a -1. It'll make more sense when we do it, but let's just get through these. Fluorine is a -1. Always, always, always doesn't ever have any other oxidation number. And we know that because we know it's that element we always stressed earlier. Remember the electronegativity number for fluorine. Fluorine is the most electronegative, always wants to gain electrons. Would never do what some of our other elements on the periodic table that are beyond fluorine do, and that is have these multiple valence or oxidation numbers. Fluorine, always a -1. Okay? Now, this is the important part that we really need to work with and give you more examples. The sum of the oxidation states in a neutral compound, one that doesn't have any charge, has to be 0. And the sum of the oxidation states if I have a charge is going to be that charge. It's going to be that charge. Now, let's do some examples. Let's do a few more examples, and I'm going to get a blank smartboard up so we can show you some of these. Okay? So, untitled. Okay, so let's try to explain, and I'm going to use the back to explain what do I mean by the sum of the oxidation numbers in a compound are 0. Once again, didn't stress this enough, the group 1 elements, our alkali metals, are always a +1. The group 2 metals in our alkaline earth are always a +2. Those ones in the middle are variable valences, variable oxidation numbers. What are their numbers? Let's use all our rules and put this together. So again, this is on the back of oxidation numbers skill sheet, and I'm under rule 5, and I'm going to work sample A, which was MgS. Now, what we don't know is, we don't know sulfur. When you peek and just try to do this quickly, you say, oh, sulfur can be a +6, +4, +2, -2. Which one is it? Let's remember, magnesium's in group 2, so it's always going to be a 2+. Now, 2+ plus what equals 0? What do you mean, what? What oxidation number? So, I have 1 magnesium, looking at the subscripts, that's a +2, and I have 1 sulfur that I don't know its oxidation number. It's going to be 0. You're going, really, Mrs. Reed, I have to show all this? No, you don't have to show any of this. You just need to get it right. And so what I want to know is what's the oxidation number of sulfur? Well, 2 plus x equals 0, and what we have then is, you move 2 to the other side, x equals a -2. So in the blanks, you're going to put Mg, tell me what 1 magnesium's oxidation number would be, and now 1 sulfur's would be a 2-. Sulfur's would be a 2-. You're like, well, that's easy, and I didn't need to show all that algebra. No, but you need to get the correct numbers in the blank, or when you're doing this homework tonight, please write those oxidation numbers above the element. So here we go. Let's do another one on the homework, and that would have been C was KMNO4. Now, what I do is I start with my bookends, my bookend elements. Oxygen, 99% of the time, is a 2-. Potassium, it's in group 1, we said earlier. Alkali metals never change their oxidation numbers, that's a 1+. The question is, what's the manganese? And that's one of the labs we're going to work on. Manganese, we can get manganese, we're going to change it all the way from +7, +6, +4, +3, -2. How do we do this? Again, you don't need to show this. Maybe some of you see the answer right away, but here's what we do. I say I have 1 potassium is a 1+ plus X. Let's name, I don't know what magnesium's oxidation number is, so I put an X for that. Don't forget for oxygen, there are 4 -2s. And so there's no charge on this compound, so it's all got to equal 0. Now, what do I do here? It's 1 plus X plus a -8 equals 0. So now, most of you can see the answer, but let's just do it. X plus a -7 equals 0. So X is equal to a +7. So again, when you answer this on the answer sheet, for the potassium, you'll put 1 plus. For the manganese, you'll put 7 plus. And for the oxygen, what each oxygen is, and that is a 2 minus. What about the charges, the ones with the charges? So let's do one more here, one more, and so this is on the bottom of this. Let's do the sample, 6 is done, 6A is done. Let's do 6B. And that is SO4 2 minus. We have a charge now. We have a charge. What is the sulfur? Okay, we know oxygen, so there's 1 sulfur, so 1 times X plus 4 times oxygen, 99% of the time, a minus 2, is going to not equal 0 this time. This time it equals the charge. This time it equals the charge. So, X plus -8 equals a minus 2. I hope you're seeing that sulfur, when it's in here, in the sulfate ion, is always a positive 6. Sulfur is a positive 6. I'm sure you're on your way to doing all these. Again, what I would like you to do is finish up all our samples. Just to point on this sheet, oxidation skill sheet, and now also on the activity 8.1, front and back. Just a little heads up, let's do one of those peroxides back under Rule 3 on redox. So, here we go, this is 3A. And what I see there is I see Na2O2. And what I have is sodium never changes. Sodium's a group 1 element. It's going to always be a 1 plus. Now, I have 2 1 pluses. I have 2 oxygens, and normally I'd put in -2, but not this time, because it is neutral. It is neutral, but now look, it's 2 plus, okay, 2 has got to, whoops, 2 plus a negative x, because this has to be my negative number here, x, lost my x, my bad, okay, so 2 is got to equal 0. So, put the 2 on the other side, minus 2x equals 2, so x, okay, divide both sides by 2, oxygen has to be a -1. Alright? That should help you now with your redox.